Jensen Huang just spent $750 billion proving that Nvidia owns the future of artificial intelligence. And in the same breath, he's pouring billions into a technology that mathematicians say could one day make everything his company builds look like a rounding error. This isn't a rival trying to take Nvidia down. This is Nvidia racing against its own shadow. To understand why this story matters, you first need to understand the scale of what's actually happening right now, because the numbers involved are almost too large to process. Microsoft alone is on track to spend more than $190 billion this fiscal year building out AI-enabled data centers. Alphabet, the parent company of Google, is planning roughly the same amount, close to $190 billion in capital spending. Most of it aimed squarely at artificial intelligence infrastructure. Meta has pushed its own spending forecast up to $145 billion. Amazon, not to be left behind, is expected to spend around $200 billion this year, primarily on AI and cloud services. Add those four companies together, and you get a number north of $725 billion. And that's before you count Oracle, before you count the smaller cloud providers, before you count the sovereign wealth funds and national governments now racing to build their own AI infrastructure. Some analysts, including teams at Evercore ISI, project that Nvidia's data center revenue alone could approach $750 billion across fiscal years 2026 and 2027 combined. Goldman Sachs, meanwhile, thinks the spending is only going to accelerate, projecting that hyperscaler capital expenditure in 2027 could land somewhere between $920 billion and $1.4 trillion. Let that sink in for a second. We are watching a single industry commit more capital in a matter of months than most countries generate in economic output over an entire year. And at the very center of that spending storm sits Nvidia. This is not a company riding a wave. This is the company that built the wave, then sold everyone the surfboards. In its most recent fiscal year, Nvidia reported revenue of $215.9 billion, a staggering 65% increase from the year before. Data center revenue alone hit $193.7 billion, which means more than 89% of everything Nvidia sells now flows through one single category: the chips, the networking gear, and the systems that power modern artificial intelligence. Quarter after quarter, the growth numbers keep climbing. Revenue up 85% year over year in one recent quarter. Data center revenue alone hitting $75 billion in a single 3-month period. Networking revenue, often overlooked, growing 162% as hyperscalers race to build the high-speed interconnects that link tens of thousands of chips together into a single functioning brain. This is the engine room of the modern internet, and Nvidia effectively owns the blueprints. It's worth pausing on just how contractual and durable this spending has become, because that's part of what separates this boom from earlier hype cycles. Nvidia's most recent quarterly revenue guide came in at $91 billion, and the company posted quarterly revenue of $81.61 billion, up 85.2% year over year, with data center revenue alone reaching $75.25 billion in that single quarter. Alphabet's cloud division grew 63% to $20 billion, with its backlog of signed contracts nearly doubling to over $460 billion. Oracle, a smaller player by comparison but growing fast, saw cloud infrastructure revenue rise 93% to $5.79 billion and booked $67 billion in new AI infrastructure contracts in a single quarter, with global GPU utilization across its fleet sitting at 97.5%. Numbers like that matter because they show this isn't speculative spending chasing a trend, it's backlog. It's signed commitments. It's capacity that's already been sold before it's even been built. Nvidia's own supply-related commitments now total $119 billion, a figure that gives the company visibility into demand, stretching well beyond the current fiscal year. And, looking further ahead, Nvidia's upcoming Vera Rubin architecture, expected in the second half of 2026, promises further gains in inference performance that could extend this entire demand cycle into fiscal year 2028 and beyond. Even competitors add weight to the story rather than undercut it. Advanced Micro Devices has lost ground to Nvidia in the AI training market, but has positioned itself more competitively around inference and agentic AI, an area where memory capacity matters more than raw compute, and where AMD's chiplet-based GPU design offers an advantage. The company has already secured 2 separate $100 billion GPU commitments tied specifically to inference workloads. Even the presence of a serious competitor like AMD underscores the same underlying point that the total addressable market for AI computing has grown so enormous that there's room for multiple winners, with Nvidia still commanding the dominant share. So when a headline says Nvidia's $750 billion bet just hit a quantum problem, the natural reaction is fear. It sounds like the empire is cracking. It sounds like some brand new technology has appeared out of nowhere and started eating away at the foundation Nvidia spent a decade building. But here's where the story gets interesting. And here's where most of the panic headlines get it completely backwards. Quantum computing isn't attacking Nvidia's data center business. Nvidia is one of the companies building quantum computing's future on purpose, with its own money, using its own hardware. Let's talk about what quantum computing actually is, because the term gets thrown around constantly without much explanation. And that vagueness is exactly what makes the clickbait headlines so effective. Traditional computers, the kind sitting in your laptop or humming away in Nvidia's data centers, process information using bits. Each bit is either a 0 or a 1, on or off, nothing in between. Every calculation, every AI model, every video you stream, all of it eventually breaks down into unimaginably long strings of zeros and ones being processed at incredible speed. Quantum computers work on a fundamentally different principle. Instead of bits, they use quantum bits, or qubits, and thanks to a strange property of quantum physics called superposition, a qubit can represent a 0, a 1, or something in between, all at the same time. Multiple qubits can also become entangled with each other, meaning the state of one instantly affects the state of another, no matter the distance separating them. In theory, this lets quantum computers explore a massive number of possible solutions simultaneously, rather than checking them one after another the way classical computers do. For certain types of problems, the difference isn't just faster. It's a completely different category of computation. But theory and reality are two very different things. And this is where quantum computing runs into its most stubborn obstacle. Qubits are incredibly fragile. The tiniest disturbance, a stray vibration, a fluctuation in temperature, even background radiation, can cause a qubit to lose its quantum state in a process called decoherence. When that happens, the calculation falls apart and the answer becomes garbage. Engineers call these mistakes errors, and reducing them is considered one of the single hardest problems in the entire field. Quantum computers today are extraordinarily error-prone, and building a machine that can reliably correct those errors at scale remains, even now, an unsolved engineering challenge. This is precisely the gap Nvidia has chosen to step into. Instead of treating quantum computing as a threat, Nvidia is treating it as an opportunity to become the essential infrastructure layer underneath it, the same role it already plays for artificial intelligence. At its GTC conference, Jensen Huang unveiled something called NVQLink, a system designed to connect quantum computers directly to classical supercomputers. The idea is elegant. Quantum machines are brilliant at exploring certain problems, but they're terrible at correcting their own errors in real time. Classical GPUs, on the other hand, are extraordinarily good at exactly that kind of rapid, repetitive calculation. So NVQLink acts as a bridge, letting the raw power of NVIDIA's GPUs handle the error correction workload that quantum processors can't handle on their own. According to NVIDIA, this system delivers 40 petaflops of AI performance at FP4 precision, with a GPU to QPU data throughput of 400 gigabits per second, and a latency of less than 4 microseconds. In plain terms, it means the classical and quantum sides of the system can talk to each other almost instantaneously, fast enough to catch and correct quantum errors before they ruin a calculation. 9 national laboratories and research institutions in the United States have already adopted this technology, including Los Alamos National Laboratory, Oak Ridge National Laboratory, MIT, Lawrence Berkeley National Laboratory, and the Fermi National Accelerator Laboratory. More than a dozen additional supercomputing centers across Asia and Europe have followed, from Japan's Global Research and Development Center for Business by Quantum AI Technology, to South Korea's Institute of Science and Technology Information, to Germany's Jülich Supercomputing Center. NVIDIA didn't stop at building a bridge. It also built a dedicated research facility called the NVIDIA Accelerated Quantum Research Center, often shortened to NVAQC. This center integrates leading quantum hardware from external partners directly with NVIDIA's own GB200 NVL72 Grace Blackwell superchips, described by the company as the most powerful hardware ever deployed for quantum computing applications. The goal is to attack quantum computing's hardest problems head-on, from qubit noise reduction to transforming today's fragile experimental quantum processors into stable, practical devices that could eventually operate at real scale. Partners at the NVAQC include Harvard's Quantum Initiative in Science and Engineering, MIT's Engineering Quantum Systems Group, and quantum hardware companies like Quira Computing. As Jensen Huang put it when announcing the center, quantum computing will augment AI supercomputers to tackle some of the world's most important problems, from drug discovery to materials development. Notice the word he chose, augment, not replace, not compete with, augment. NVIDIA has also moved beyond hardware and into the software layer, releasing an open source collection of AI models called Ising, specifically designed to help quantum computers become more useful in real-world applications. The core insight here is almost poetic in its symmetry. Nvidia is using the very technology it dominates, artificial intelligence, to help solve quantum computing's biggest weakness, which is error correction. It's the same playbook the company used to conquer the AI industry in the first place. Build architecture so good, so deeply integrated with your own hardware, that anyone serious about the field has no real alternative but to build on top of what you've created. And Nvidia didn't stop at software either. It has taken direct financial stakes in quantum hardware startups, including a partnership with and investment in the French company Alice and Bob, a firm focused specifically on developing error-resistant qubits, one of the most promising approaches to solving quantum computing's core reliability problem. This puts Nvidia in direct proximity to companies like Microsoft and IonQ, both of which are pouring resources into their own quantum computing progress, turning what used to be a niche academic pursuit into a genuine corporate arms race. So here's the real question. If Nvidia is investing so heavily in quantum computing, doesn't that prove the technology really is coming for its core AI data center business? This is where the physics and the economics both say, emphatically, not anytime soon, and probably not ever in the way the headlines imply. The mismatch between quantum computing and AI workloads isn't a matter of opinion. It's a matter of raw physical scale, and the numbers make the gap almost comically large. A single rack of Nvidia's most popular AI training chips draws somewhere between 120 and 140 kilowatts of power, and the next generation of systems is projected to push that figure past 200 kilowatts per rack. Now multiply that by the size of an actual hyperscale AI campus, which can contain tens of thousands of these racks. Total power consumption for a single facility can reach hundreds of megawatts. And some of the largest AI campuses currently under construction are projected to eventually draw a full gigawatt of electricity, roughly the output of a large nuclear power plant, dedicated entirely to running artificial intelligence workloads. Now compare that to quantum computing. A quantum machine capable of supporting a couple thousand qubits, which is roughly the current frontier of the technology, runs on approximately 30 kilowatts of total power. 30 kilowatts? That's a rounding error compared to a single AI training rack, let alone an entire data center campus. This power gap reflects a much deeper truth about what these two technologies are actually built to do. Artificial intelligence training and inference run on classical hardware because the underlying math, matrix multiplication, performed across enormous data sets is precisely the kind of repetitive, parallelizable workload that GPUs were engineered to devour. Quantum computers are, quite simply, bad at that kind of work. They cannot absorb AI's compute demands, they cannot run AI workloads more efficiently than classical chips, and they cannot substitute for the kind of processing that trains a large language model or powers a real-time AI assistant. This isn't a temporary limitation waiting for better engineering. It's a fundamental mismatch between the type of problem quantum computers are good at solving and the type of problem modern AI actually needs solved. There's a persistent assumption floating around in tech media, and sometimes even in investor pitches, that quantum computing will do for artificial intelligence what GPUs once did, that it will simply drop into existing systems, speed everything up, and reshape the economics of the entire industry overnight. But that's not what the engineers and researchers actually building these systems say when you ask them directly. What they describe instead is an entirely different category of machine, designed to solve an entirely different category of problem. Quantum computers excel at a narrow, specialized set of challenges that classical computers either struggle with or simply cannot solve at all, no matter how much raw power you throw at them. Designing new battery chemistries for the next generation of electric vehicles and grid storage is one such problem. Modeling complex molecular interactions for pharmaceutical drug discovery is another, since simulating how molecules actually behave at the quantum level requires quantum tools to do accurately. Quantum computers are also being explored for designing more efficient photovoltaic cells that convert sunlight into electricity, and for optimizing massive financial portfolios or pricing complex derivatives in ways that could give financial institutions a genuine competitive edge. And in a more unsettling application, the same quantum machines being developed for scientific breakthroughs also have the theoretical capability to break the encryption standards that currently secure most of the internet, which is exactly why governments around the world are treating quantum computing as a matter of national security, not just scientific curiosity. None of these applications look anything like training a large language model or running a chatbot. They're specialized scientific and financial tools, useful in specific high-value domains, not general-purpose replacements for the kind of computing that powers the modern AI economy. And that's precisely why Nvidia feels comfortable investing in quantum computing while simultaneously pouring hundreds of billions of dollars into classical AI infrastructure. These aren't competing bets on the same outcome. They're complementary bets on two very different futures that happen to be arriving at the same time. And Nvidia wants to be the essential infrastructure provider for both of them, not forced to choose between them. Still, that doesn't mean Nvidia's massive AI bet is without real risk. It's just that the actual risk has almost nothing to do with quantum computing and almost everything to do with old-fashioned financial mechanics. As hyperscaler spending has ballooned past $700 billion for 2026 alone, with some projections pushing toward $1.4 trillion the following year, investors have started asking a very reasonable question. Where exactly is all this money coming from? The answer, increasingly, is debt. Reports indicate that hyperscalers are gearing up to spend over $750 billion on AI data center infrastructure this year, with that figure potentially climbing toward $870 billion in 2027, and that level of capital expenditure is expected to exceed the free cash flow of even the largest hyperscalers in the world. When spending outpaces cash flow, companies borrow, and the market has taken notice. Nvidia's 5-year credit default swap spreads, essentially the market's price for insuring against the company defaulting on its debt, widened to 57.25 basis points, up from roughly 42 basis points just a few weeks earlier. That might sound like a small technical shift, but for a company sitting on approximately $50 billion in cash, it's a meaningful signal that some investors are pricing in more financial risk than they were before. Nvidia responded to this environment in a very telling way. The company announced plans to issue between $20 and $25 billion in high-grade bonds in mid-June of 2026, its first bond issuance in 5 years. For a company that has historically funded itself through operating cash flow rather than debt, that alone was a notable shift. But the market's reaction told an even more interesting story. Demand for the bond offering reportedly reached $85 billion, roughly 4 times the amount Nvidia was actually trying to raise. That kind of oversubscription suggests that even as some analysts and credit markets flag rising risk, the broader investor base still has enormous confidence in Nvidia's long-term position at the center of the AI economy. It's a snapshot of an industry pulling in 2 directions at once. Genuine caution about how the spending is being financed, alongside genuine conviction that the underlying business remains extraordinarily strong. Zoom out far enough, and the picture that emerges isn't one of collapse or disruption. It's one of convergence. Nvidia isn't watching quantum computing erode its AI empire from the sidelines. It's actively building the connective tissue between 2 computing paradigms that are both still in their early stages of maturity, positioning itself so that whichever direction the future bends, classical AI, quantum computing, or increasingly likely some hybrid combination of the two, Nvidia's hardware and software sit somewhere in the middle of it. That's not a defensive move made out of fear. It's the exact same offensive playbook the company has run for over a decade. Identify the computing paradigm that's about to matter, build the infrastructure layer underneath it before anyone else does, and make it so deeply integrated into the ecosystem that competitors are left playing catch-up for years. The broader numbers around AI spending only reinforce how enormous this moment actually is. Market research firm Gartner estimates total worldwide AI spending will land somewhere between $2.52 trillion and $2.59 trillion in 2026 alone, representing year-over-year growth of somewhere between 44 and 47%. Gartner also identifies infrastructure, the physical data centers, chips, networking equipment, and power systems, as the single largest category within that spending, accounting for well over 45% of total AI expenditure worldwide. Goldman Sachs has framed the broader hyperscaler capital expenditure cycle from 2025 through 2027 as likely to reach $1.15 trillion, more than double the total spent across the 3 years before that. To put that scale in perspective, some analysts have noted that the combined 2026 capital expenditure projections for just the 5 largest technology companies now exceed the entire gross domestic product of all but the top 20 national economies on the planet. This isn't incremental growth. It's a wholesale restructuring of where global capital flows, comparable in scale to historical infrastructure, booms like the railroad expansions of the late 1800s, according to some of the same analysts making these projections. So where does that leave the original headline, the one claiming Nvidia's $750 billion AI bet just hit a quantum problem? It leaves it mostly as an exaggeration built from 2 very real, very separate stories stitched together to generate clicks. The first story is completely real. An unprecedented historic wave of capital spending on artificial intelligence infrastructure, with Nvidia sitting at the absolute center of it, converting that spending into record-breaking revenue quarter after quarter. The second story is also real. A genuine, well-funded, strategically important push by Nvidia into the world of quantum computing, complete with dedicated research centers, breakthrough connectivity technology, direct investments in promising startups, and open-source software built to solve quantum computing's hardest technical problems. What's not real, at least not yet and not any time in the foreseeable future, is any meaningful collision between these two stories. Quantum computers are not draining workloads away from Nvidia's data centers. They're not becoming cheaper or more efficient substitutes for AI training. They're not threatening the fundamental business model that turned Nvidia into one of the most valuable companies in the world. Instead, quantum computing is emerging as a complementary technology, one that Nvidia is deliberately positioning itself to control the infrastructure for, using the exact same strategy that made it the undisputed leader of the AI revolution in the first place. It also helps to remember how Nvidia got here in the first place, because the parallel is almost too clean to ignore. 2 decades ago, graphics processing units were considered niche hardware built for rendering video game visuals, nothing more. Nvidia made a long, patient bet that the same parallel processing architecture used for graphics could be repurposed for general scientific computing, and it built an entire software ecosystem around that idea called CUDA. For years, that bet looked unremarkable. Then, artificial intelligence research exploded. Deep learning models needed exactly the kind of massively parallel computation GPUs were built for, and virtually overnight, Nvidia wasn't a graphics company anymore. It was the single most important company in computing. CUDA, the software layer nobody outside of academia cared about for years, became one of the deepest competitive moats in the entire technology industry. Because by the time rivals tried to catch up, an entire generation of AI researchers had already built their careers, their code, and their institutional knowledge around Nvidia's platform. That same pattern is now playing out again with quantum computing. Nvidia isn't waiting for quantum machines to become commercially useful before it shows up. It's embedding itself into the research process right now, while the field is still young, while the standards are still being written, and while the researchers who will define the next 30 years of quantum computing are still deciding which tools to build their careers around. Whether or not quantum computing ever becomes a trillion-dollar industry on its own timeline, Nvidia is positioning itself so that if it does, the infrastructure underneath it runs on Nvidia hardware and Nvidia software, the same way so much of today's AI infrastructure already does. That's not a company reacting to a quantum problem. That's a company writing the opening chapter of quantum computing's origin story before its rivals have even finished reading the headline. The real risks facing Nvidia's massive AI bet are financial and structural, not technological. They involve questions about debt financing, about whether hyperscaler spending can continue outpacing free cash flow indefinitely, about market concentration in a handful of companies making bets so large they now rival national economies, and about whether the extraordinary growth rates driving all of this capital expenditure can be sustained as the initial AI build-out matures into something more measured. Those are legitimate concerns worth watching closely in the months and years ahead. But quantum computing isn't one of them. If anything, it's a signal of confidence, a bet that whatever comes after today's AI boom, Nvidia intends to be standing at the center of that story too, just as it is standing at the center of this one. The data center race isn't slowing down, and it isn't being derailed by some quantum surprise attack. It's expanding, layer by layer, technology by technology, with the same company building the foundation underneath almost all of it.